Hello everyone. So this is basically a part of a digital assignment based on the applications of linear algebra. So over here I'll be discussing a particular application of linear algebra, that is cryptography. So okay, let's begin. So for those of you who don't have any idea of cryptography, you first need to know these basic terms, which is plaintext, ciphertext, encryption and decryption. So I have included all the relevant definitions over here. So cryptography is basically the conversion of plain text into ciphertext, which is an unreadable text. So it is desired for security purposes. So now we'll be learning the various methods of encryption. So one of the most earliest methods of encryption, which is also cryptographic technique, is the substitution cipher technique. So what do we do in substitution cipher technique is that we'll be given with a plain text and we'll be randomly shifting it by an integer k. First of all, we'll be converting this plain text into its numerical equivalent. So let me show you by an example what do we do in substitution cipher. For example, we'll be having a plain text, we will meet at midnight, and we will be given a key. For example, in this case, the key is taken as 11. So what we'll be doing at first, we'll be converting this plain text into its numerical equivalents. For example, the numerical equivalent for W is taken as 22, for E it is taken as 4, and so on. Now what we'll be doing for encryption purposes is that we'll be adding the value K using the reducing modulo 26 operator, and we'll be converting this into this particular sequence, and again we'll be converting this into the alphabets back again, so we'll be getting this text which is our cipher text. Now for decrypting purposes of using this cryptographic technique, we'll be subtracting the same key from the numerical values that we get. So as you can see, this particular cryptographic technique is very weak and it can easily be broken down by hackers. Using brute force technique, this method can easily be broken down by the hackers who want to steal our information. So we need to adapt or go to a higher level of cryptography, and for that purposes, what do we do is that if you want to make the substitution cipher strong, what do we do? That we take a set of keys instead of just a single key, and we add this set of keys with the numerical values of our alphabets. So by doing this, we increase the security by a large amount. But still, if the hacker wants to access the information, he can easily do it by using the brute force technique on various keys possible. So we'll be taking the cryptography to a completely new level with the introduction of linear algebra and matrices as keys, which I'll be covering in the next session. So here is the theory related to how do we use matrices for the purpose of encryption. So let us cover all the points one by one. So what do we do first is that we again convert all the plain text alphabets to the numerical values. Then what do we do is that the values are separated into vectors. The values that we'll be getting, we'll be separating them by vectors and will be arranged in a matrix form. The next step that we do is that, okay, Okay guys, so now we'll be seeing the complete process of encryption and decryption using matrices and applied linear algebra. So this is the complete process of encryption over here. So you can basically give it a read. I'll be explaining each and every point with the help of a suitable example. Similarly, this is the complete process of decryption. You can again give it a read. I'll be explaining all the points thoroughly with the help of a suitable example. So before jumping directly into the example, I'd like all of you to just remember this particular table. This table is used for the purpose of converting the alphabets of the plain text that we will be getting into the numerical equivalents. For example, A's numerical equivalent is 0, B has a numerical equivalent as 1, and so on. Similarly, for if we'll be encountering a space in between our particular plain text, then we'll be using the numerical equivalent of 26. Okay, so now let's jump into the example. So this is our very first example. The plain text that we have over here is Elvis has left the building, and this is our encoding matrix. So the very first thing that I want all of you to realize is that the encoding matrix in this particular case is same as the value of k in case of the substitution cipher. We'll be using this encoding matrix for the sole purpose of converting our plain text into ciphertext. Okay, so now let's jump into the process of encryption. So the very first step that you need to do is that you need to convert this plain text into the numerical equivalent, the sequence of numerical equivalent values as I've shown over here. We'll be using the same table that I've shown you for this purpose. We'll be converting the plain text into numerical equivalent. So this is our first step. Now the second step, we will be making vectors of row size 3 from the sequence that we have just obtained. As you can see over here, we have made vectors of row size 3 from the sequence that we have obtained earlier, 4, 11, 21. So the reason for row size 3 is that the row size need to be same as the row size of the encoding matrix. So over here we have the row size as 3. So we will be forming vectors of row size 3 over here also. Now the third step is we'll be combining all these vectors and we will be multiplying it with the help with the encoding matrix. So this is basically a basic matrix multiplication. The answer to this multiplication is shown over here. Now the fourth step is we will be again separating the vectors of this matrix just like we have done over here. We'll be separating the vectors of this particular matrix. Let me show you how. In this manner, we will be separating the vectors of this matrix. So now the fifth step, what we will do is that we'll be arrange all the numerical values of this vector again into a sequence. Now this particular sequence represents our ciphertext. But as you can see, minus 27 has no place in the table where I was converting numerical values into alphabets. So to get these values, the negative values, as well as the values which are greater than 26, we will be applying the modular arithmetic operator. We'll be basically taking the mod of all these values with 26. So the resultant sequence will be like this, and this over here is ours when we will convert this particular numerical values into alphabets using the table that I have shown you earlier. This particular alphabet sequence is our ciphertext. So this is a complete process of encryption. We have converted our plain text, that is Elvis has left the building, into a ciphertext. So let me just revise the complete process again. Firstly, we'll be forming the sequence. Nextly, we'll be multiplying the vectors obtained by the encoding matrix. The next thing we'll be doing is we'll be arranging the multiplied matrix back into a sequence of numerical values. We'll be applying modular arithmetic and we'll be getting the ciphertext as here. Okay, so this is the complete process of encryption. Now we'll be moving to the process of decryption. So the process of decryption is very much similar to the process of encryption. We'll be following the exact same sequence of steps as we have followed in case of encryption. So the very first step that we followed in encryption was converting the sequence of alphabets into the numerical equivalents. So this is our ciphertext. We will be converting the ciphertext into the numerical equivalents. So this is our first step. The second step that we followed in encryption was to arrange this sequence into vectors of row size 3. So the same process I have done over here. I've converted the sequence into vectors of row size 3. The third step in the process of encryption was multiplying these sequence with the encoding matrix. But over here, as we are decoding the ciphertext back into the plain text, we will be multiplying it with the inverse of encoding matrix. So for the purpose of getting inverse, you can use various linear algebraic methods. For example, you can use Gauss-Jordan method for obtaining this inverse. So once you have obtained the inverse, you will be multiplying it with the sequence of the vectors that you have obtained. So this is the result multiplied of the matrices over here. So the again we'll be following the same steps as we have followed in case of encryption. We'll be separating the multiplied matrix back into vectors of row size 3. So over here I have separated it back into vectors of row size 3. Again, I'll be arranging all these vectors into sequence: 108, 63, 73, 108, 63, 73, 34, 18, 26, 34, 18, 26. So like this, I'll be arranging them into sequence of numerical values. So again, as you can see that if I want to convert this back into alphabets, there is no such alphabet for the value 108, so I need to get this value in the range of 0 to 26. So that for that particular purpose, I'll be again using the modular arithmetic, and I'll be taking the mod of all the values which are greater than 26. I'll be taking their mod with 26, so I'll be getting this particular sequence. Now if you observe this sequence carefully, 4, 11, 21, 8, this is the same sequence that we got when we converted our plain text into the numerical values. So let me show you. This was our plain text. Elvis has left the building, and when we converted it into numerical values, we got the same sequence: 4, 11, 21. So even after the process of decryption, we are supposed to get the plain. We are supposed to get back the plain text. So over here, we have got the same sequence as we have got from the plain text. So this basically represent our plain text. So this completes the process of decryption. So now I'll be taking many more examples for complete understanding of the subject. Okay guys, so for better understanding, I've taken another example of cryptography over here. So over here, the plain text that I have is good luck, and the encoding matrix is denoted by A. This is over here, this is our encoding matrix. So we'll be following the exact same procedure, exact same steps as I have followed in the previous example. So the very first step was to convert all the alphabets into numerical equivalents. So over here I have converted all the alphabets of my plain text, that is good luck, into the numerical equivalents. Okay, so the second step was to organize the sequence of numerical equivalents into vectors of row size equal to the row size of the encoding matrix. So over here we have our encoding matrix. Its row size, as you can see, its row size is 3. So we have arranged it into vectors of row size 3. Now, the third step was to multiply the vectors obtained with the encoding matrix to get the ciphertext. So over here I have shown the multiplication of individual vectors. So this over here is the result of multiplication, and this represents our cipher matrix or the ciphertext, as we say. So now this was the complete process of encoding. We have taken the plain text and we have converted the plain text into the cipher matrix or the ciphertext, as we say. Now for decoding, as I have stated earlier, we will follow the exact same steps, but this time we'll be multiplying the matrix with the inverse of the encoding matrix. So in a previous example, as I have said, that you can find the inverse using linear algebraic methods, for example Gauss-Jordan. So over here I've demonstrated the process of Gauss-Jordan. So basically what we do in Gauss-Jordan is that we try to convert the given matrix into the final identity matrix using a set of row operations. So over here the row operations are stated. You can apply these row operation on this particular matrix and you will be getting a identity matrix. So the matrix that you got alongside the identity matrix after these row operations represents the inverse of the matrix that you have started with. So this is basically the inverse matrix we have with us. We have calculated the inverse matrix using the linear algebraic method of Gauss-Jordan. So now we'll be using this inverse matrix for the purpose of decryption. Okay, so we have our vectors over here. These are the vectors from the ciphertext. You can see this is the ciphertext matrix. So we are multiplying the inverse of encoding matrix with the ciphertext matrix, and the result that we are getting represents the plain text. Okay, so you can basically multiply all the ciphertext vectors with the encoding inverse of encoding matrix, and you will be getting the plain text vectors. So I have assembled all the vectors over here: 6, 14, 14, 3, 26, 11, 22, 10. And if you convert these numerical values back into alphabets, you'll be getting the same plain text, that is good space luck. Okay, so in this way we do encoding and decoding using cipher metrics, or more precisely we can say using linear algebraic methods. So this is all about the examples that I want to con Okay, so now I just want one last concept I want all of you to know, and this will be really helpful, especially when you will be solving a number of problems on cryptography using matrices. So the concept is that there will be a number of cases when the plain text that you will have, when you will be converting this plain text, for example, you have the plain text as COVID, and because the encoding matrix that you have is of row size 3, you will have to generate the sequence, and the vectors that you will have to generate from this sequence should also be of row size 3, as I have already explained in the previous two examples. But as you can see, we only have 5 alphabets in this case, COVID. So we just have 5 alphabets and we need to form vectors of row size 3. So the first one we can easily form using the alphabet COV. We can form this vector 3, 5, 15, 22. But for the second vector, that is, we are just left with ID. We are just left with 2 alphabets and we need to form vector of row size 3. So what do we do in such cases? We add an additional 0 if we are short of alphabets with us. So okay, so for I we have the numerical value as 9, for D we have the numerical value as 4, and as we have to form vectors of row size 3, so we'll be adding an additional 0 from our side to complete the row size of the given vector. So the further process of encoding and decoding is exactly the same. We'll be multiplying these vectors with the encoding matrix, and the resultant vectors that we will be getting will form the ciphertext. So this is all that you need to know for the purpose of using cryptography using linear algebra and matrices. So finally, I would like to highlight the references that I've used for maintaining and developing the resources of this particular video. These are the references, and I would especially like to thank my professor, Dr. Ramesh Kumardi, for providing me the opportunity of present in front of you the complete process of cryptography using linear algebra. Thank you everybody for watching the video.